Hello, my name is Brian Geiser with Kamika Instruments. Today, I'd like to give a brief update on our newest reconstruction efforts, a reconstruction based on a fully 3D electrostatic optical model. Standard APT reconstruction is based on a spherical apex model to which detected ions are back projected according to an approximate projection law, and the spherical geometry is used further to compute depth increments and sometimes apex evolution. In real life, apex shapes can be quite aspherical, and inhomogeneous specimens can evolve with substantial shape changes throughout the course of an acquisition. Since we are currently restricted to a spherical apex, we can't really accommodate some of those shape changes, and the resulting incorrect back projection can cause important artifacts like unphysical density variations. To make substantial improvements in these cases, we need to break away from the constraint of using a spherical apex model. To that end, we have been developing a set of software that builds a numerical model of the most important optical elements of an atom probe, namely the actual specimen itself, whether it's a wire specimen or a microtip, and optical elements very close to the apex of the specimen, like the local electrode. With this model, we can impose apex features that cause non-uniform magnification. Then we solve the electrostatic environment and propagate ion trajectories through the model to build a map of where ions evaporated from the apex end up on the detector. For a more detailed description of our model and reconstruction procedure, please see the presentation at the link shown at the bottom of the page. Since our last presentation, we have been working to make the model more flexible. One aspect where we have done that is in the specification of the shank geometry. We were previously limited to modeling the shank geometry with two discrete sections of different shank angle. We can now support an arbitrary profile, and if the profile has been previously defined in an IVAS or AP Suite tip profile reconstruction, we can directly import that into the electrostatic model of the shank. We had previously discussed the idea of reconstructing to an equilibrium apex that can be built using the software, or if desired, a spherical apex, but now trajectories will be propagated through a simulated electric field, rather than following a point projection model. We now have a few different ways that a non-uniform apex shape, or rather a set of shapes, can be defined for a reconstruction. On the left, we show an apex that has been specified by a simple radial profile. It is assumed to be azimuthally symmetric, and the profile shape is just swept around the apex center. The top image on the left shows how trajectories from uniformly spaced launch sites on the apex map to the detector. You can see that the concave shape we've imposed on the apex results in a pattern of low and high density on the hip map. For planar features and a cross-section orientation, we now also support the use of a full diameter profile that directly modifies an equilibrium or spherical shape with a height modulation. Here we have imposed a slight concave groove through the center of the apex and show the trajectory maps that result from these models. We hope that these tools would be useful in different ways to a range of users, depending on how much information about the apex and specimen geometry is available for use in reconstruction. If no additional data is available, we would expect the equilibrium apex model to offer more realistic projection than the current spherical model. In the case of structured material, we are hopeful that incorporating the evolution of apex shapes through evaporation simulations might provide qualitative reduction in evaporation artifacts. Ideally, we would be able to take advantage of complementary modalities to learn the ground truth of what the apex shape is during an APT analysis, using a sequence of high-resolution images to drive the electrostatic model through shape changes. We are currently in the process of supporting the use of an externally generated full apex model to define the electrostatic geometry, like this AFM image of an oxide layer in silicon, oriented in cross-section. As expected, the higher evaporation field oxide settles into a higher curvature feature than the rest of the silicon apex. This results in an over-magnified oxide layer in the reconstruction. Shown on the right are a standard spherical reconstruction and the improved accuracy achieved just by imposing a simple approximated fixed 1D profile in the apex geometry model. For more details on how this great AFM data was obtained, I encourage you to view Claudia Fleischmann's presentation Wednesday afternoon. I'd like to conclude by thanking my collaborators, with a special mention of Joe Bunton, who is the originator of a lot of this software, and especially the IMEC folks for their fantastic AFM data. Thanks for your attention.